Why are WebSockets so much more complicated than everyone thinks? Well, because there are some edge cases, which I depicted here, that can lead to more complicated situations that you might need to handle. Well, luckily I have solutions for those, or like the industry actually has solutions for those. So that's what we're gonna learn in this video. And we're also gonna take a look at the code as well. So before diving deep, let's understand in a short version summary of WebSockets. So let's try to understand how it works. Basically, the server and the client establishes a socket connection, meaning we're not making multiple requests back and forth anymore. We establish one socket connection and can exchange the data between it. So the client can send the data to the server real time and the server can respond real time. And this is one of the examples actually of messenger applications. We have multiple clients that connect to the same server. Maybe they can even talk to each other. I'm not sure. Maybe that's a different version of those kind of apps. But usually these clients are going to send the server the data, and the server can then reroute this data to a particular client that's also connected to it on another end. So this is one of the ideas. Another idea can be just a client that connects to the server, and the server gets live data from somewhere, for example, some kind of a live tracker, let's say the weather app, because the weather constantly updates, the estimations are being updated, and the server is going to push this data into the client. All right, so this is the WebSockets in a nutshell. Now let's start to understand the difficulties, where these difficulties can occur. So let's say we have a client that already connected to a WebSocket, okay, and the WebSocket sends the data back, but sometimes it happens that the server simply crashes, okay? So what happens when the server crashes? The client can either detect that the server has crashed. This is the best case scenario, but most of the times actually this does not happen, because when the server crashed, it's not able to close the connection properly. And that's why we need to use this thing called heartbeats, or in other words, simply send a ping request from time to time to the server, and the server has to reply with a pong. And if the client detects that the pong didn't arrive within 10 seconds, because this is what we're expecting, then we might try to close the connection manually on the client and try to reconnect. Okay, let's look at a simple example. So let's say we have a Node.js app and we're using WebSockets. So what we're gonna do here is we're going to have an health check endpoint first of all as well, but also as soon as the server knows that there's a client connected, we log it out and we're waiting for messages. So every time a message arrives, we can send a pong back. And of course, you can see that if something happens, we can close it automatically. But if there's some kind of an error occurring in this logic, we're sometimes not even able to reach this block of code. Okay, this is the problematic part. And the client is going to look like this. We have a button, let's say in the HTML. As soon as the socket opens, we're constantly logging this out. We're sending the pending data. Why are we sending the pending data? Because while the connection is broken, client can actually do some smart stuff. For example, we can save it in a local storage here while the data has been updated. And then as soon as the connection restored, we can take this data and send it back to the server from the local storage. So this is what it's doing. On a message, every time the pong is received, we're gonna update the last pong time. And here, every time we're sending a ping, we actually compare whether the ping has been, or the pong has arrived within the last 10 seconds. If no pongs have arrived, we try to close and reconnect. All right, otherwise we're gonna send ping again. So let's start this application and see how this is working. I'm gonna go inside heartbeats example and say node server.js. This is going to run, and I'm also going to go live with this HTML website. We're gonna see that in the network tab, if I refresh the page one more time, we're gonna see that there's a WebSocket connection and on this local host, and they're just exchanging pings and pongs here. So every 5 seconds, there's gonna be a ping and a pong. And I'll just go to the code really quickly and let's turn this off. I'm gonna go to the server and say, instead of a pong, which we're expecting, I'm gonna send a pongo, right? Find a name. I'm gonna go live again. And now when the application boots up, heartbeats example, I'm gonna turn on the developer tools, and we're seeing that we're receiving a pongo. So there's no pong. So no pong received in 10 seconds, reconnecting, and we connected again. But since I'm sending pongo every time, it's gonna disconnect automatically from the front end and try to connect again. So you basically get the idea. This is how we can make it more false tolerant. I'm gonna push all of this code so that you can check it in your free time or from GitHub. All right. Now let's talk about the second use case, which is more interesting. We're gonna be using server sent events here. So every time our WebSocket API is down, instead we can use a fallback called server sent events. Sorry. What is server sent events? It's almost like a WebSocket. If we actually Google it, we're gonna get a lot of articles that are trying to compare WebSockets to server sent events, and we're gonna see that both are capable of pushing data to browsers. However, they're not the competing technologies. WebSockets connections can both send data to the browser and receive data from the browser. A good example of an application that could use WebSockets is a chat application, as I said earlier. Server sent events, on the other side, are connections that can only push data to the browser, meaning online stock quotes, Twitter updating timeline, and so on. All right, we cannot send the events to the server sent events. Of course, we can define a specific API route for this, but it doesn't work as a connection like in a WebSocket. Okay, but we still can randomly receive events from the server. Now, what is it gonna look like? So we're gonna send a ping, and let's say the pong doesn't arrive. So this is gone. And after some time, let's say we're gonna send another ping, and after 2 tries, we don't receive a pong back. We're gonna abandon this for some time and switch to server sent events. And of course, the server has to be able to handle that. So let's see SSE example. We have an index.html. So the server actually looks quite interesting as well. We're gonna send a pongo just to trigger this error. And we have a fallback with the events endpoint. This is not necessary, but if you want something reliable, you can of course do that. And we're simply gonna send some data to the client. And of course we can close it too. On the client, on the other hand, is something new. So we not only have WebSockets here, but we also, if I scroll down here, connect SSE. This is the fallback that's gonna happen. So we're gonna connect under this URL, under events, and we're simply going to, the API is looking quite similar to the WebSocket. So on message, we're gonna say something was received. On error, an error happened. Again, interesting fallback. Let's quickly see how this is going to work. Oops, I turned it on too quickly. I'm gonna start the server first. I'm gonna go back. I'm gonna go into SSE example, node server.js, and now we can go live with this file. All right, and as you can see, connected via WebSocket. Now we received a pongo, tried to send another ping, failed attempts 1, and we're waiting for another attempt that's gonna fail. And let's fail it again one more time. Yeah, failed attempts 3, and now we switch to SSE fallback. And now, as you can see, we're receiving events from the server sent events. So how cool is that? Another reliable method of dealing with flaky WebSockets. All right, I'm gonna close this one. And again, you can find all of this code on GitHub. Alrighty, another common method is having a load balancer between your servers. This is probably what you're definitely gonna have, because you're not gonna have a WebSocket on one server, although this is also common to avoid all this complexity. But let's say you're trying to scale horizontally. So you're gonna create another WebSocket API. And if one of them is down, let's say the load balancer is going to create another one. Okay, so how is this going to work? First of all, we're going to use the least connection method, so not round robin. And every time the load balancer knows that one of the services is down, it's still at least going to try to allow some fails. And after the failure has been detected for 10 seconds, it's only then going to create another copy of this just to make sure that the client can reconnect. And the client only knows the URL of the load balancer. It cannot directly communicate to the WebSocket API. Okay, so this is also handy. Now, another thing is, for example, we have 2 running APIs at the same time. So here in this example, we only had one, and we can automatically auto-scale horizontally if needed. But in this case, we already have two for one or other reason. If the client establishes a connection with one API, how do we know that the next time the client tries to reconnect, it's going to hit the exact same server and not this one? Well, we can make sure that we use sticky sessions, for example, in Nginx. This is the Nginx configuration file, by the way. We're going to use IP hash. This means we're going to have a sticky session, and every time the load balancer tries to reroute this request from the client, because Nginx is going to actually connect the hash in the cookies when talking to this client, and the client is also always going to send a cookie, then the load balancer knows, aha, this client was previously connected to this server, so I'm going to try to send the same request to here. Or this was the example of a cookie, by the way. This is the cookie where you can say it can expire, and this is the hash that it hashes, I believe, based on the user's IP. Okay, how cool is that? Well, another and final example is the example of broadcasting. So let's say the client is talking to this particular API, but in broadcasting, as you know, the broadcast server wants to send a message to all the clients, meaning not only this client as it is now, but also this client. But this client is not connected to this API. It's maybe connected to this one. So how can one API broadcast a message to all the APIs? Again, just imagine a use case of a chat. Luckily, we have message brokers such as RabbitMQ. Okay, RabbitMQ can be used, Redis can be used, many things, but primarily RabbitMQ, in my opinion, is the best for that. So one API can send an event through RabbitMQ connection to another service, and then this service also can pick this message up and basically send the same event or same message to its connected clients. Okay, so in this case, this client is going to be connected to this one, and then it's going to receive the same exact message, maybe not real time, but near real time. All right, let's take a look at the code of the broadcasting. We only have two servers here, no clients. So every time we're going to establish AMQP connection, we're going to create a channel. And in a channel, if there was a message, we're going to take the contents of a message and broadcast it to the client, to the WebSocket client like this. Okay, nothing complicated. That was very simple. And basically the server 2 is doing pretty much the same story here. All right, if you guys learned anything new, and if you learned anything new about WebSockets and its resilience, just let me know down in the comments, and smash like and subscribe, and I'm gonna see you very soon.